Hello, I'm Mrs. Stevenson. Induced EMF. A straight wire, 0.20 meters long, moves at a constant speed of 7 meters per second, perpendicular to a magnetic field of strength 8 times 10 to the minus 2 Tesla. A. What EMF is induced in the wire? B. The wire is part of a circuit that has a resistance of 0.50 ohms. What is the current through the wire? And C. If a different metal was used for the wire, which has a resistance of 0.78 ohms, what would the new current be? Well, let's first look at our diagram. We set up our coordinate system so that the upward directions are positive y values, to the right are our positive x values, and that coming out of the screen towards you are the positive z values. We have our wire, which has a length of 0.2 meters long, and it's moving with a velocity of 7 meters per second to the right, and it's connected to an ammeter to read the current. These green dots represent our magnetic field. Because they're solid dots, it's saying that the magnetic field is coming out of the screen towards you, so that the wire is moving perpendicular to the magnetic field which is coming out towards you. Whenever a piece of wire moves through a magnetic field, a current is induced. You can use an ammeter to measure that current, or you can calculate it using Ohm's law. And so we want to determine what EMF is induced in the wire. So we're going to write down our known values for the problem. And we know that the velocity of the piece of wire was 7 meters per second. We know that the length of the wire was 0.20 meters. Our magnetic field strength was 8.0 times 10 to the minus 2 Tesla. We know that the resistance of our first part of the circuit was 0.50 ohms. And we know the resistance of the new piece of metal was 0.78 ohms. Scroll down so we can list our unknowns. We are looking for the induced EMF as well as the current in our wire. Now, in order to solve for our induced EMF, we are going to be using the equation that EMF is equal to the magnetic field strength times the length of the wire times the velocity of the wire. This is what we're solving for, and we have known values for each of our variables on the right. So our induced EMF is equal to our magnetic field strength, which was 8.0 times 10 to the minus 2 Tesla, times the length of our wire, which was 0.20 meters, times the velocity that wire was traveling through the magnetic field, which was 7 meters per second. When we calculate this out, we see that we get an induced EMF that equals 0.11 Tesla meters squared per second. Now, a Tesla meter square per second is just another way to write a volt, so we can write our answer as 0.11 volts as our induced EMF in the wire. Next, we want to calculate the current within this wire. We're going to go back to Ohm's law. Ohm's law says that the voltage is equal to the current times the resistance. Because we're solving for current, we want to have current by itself on one side of the equation, so we're going to divide both sides by the resistance, canceling the resistance out on the right. So we are left with a rearranged Ohm's law equation stating that the current is equal to the voltage divided by the resistance. So let's plug in our known values. We just figured out the induced EMF for the circuit, which we can put in for our voltage because we had the units of volts, which was 0.11 volts, divided by the resistance of our wire, which was 0.50 ohms. So we find that the current within that wire was 0.22 amps. And using the fourth right-hand rule, we can tell that the direction of the current is counterclockwise. Lastly, we want to determine the current in our different piece of metal. And so we are going to take Ohm's law that we rearranged for current, but remembering that for our voltage, because we found our induced EMF written in terms of volts, you can also think of it as being the induced EMF divided by the resistance to help you solve for your current. So our current in the new piece of metal, again, we determined our induced EMF was 0.11 volts. We're going to divide by the new resistance, which was 0.78 ohms. And we find that the current within the new piece of metal is 0.14 amps. And again, using the fourth right-hand rule, we find that the current is counterclockwise.